Hi, my name is Alberghini and I'm a second-year PhD student. In this short video I will present you my research activity about porous smart materials for passive devices, which was developed in collaboration with the MIT. So I will start introducing the context behind the research. So what are passive devices? They are characterized by the absence of any mechanical moving parts, such as pumps, and their working principle is based on different types of physical phenomena. There are several reasons why we want to go passive. For example, they are low cost and optimal for off-grid installations, and they can be used for a very wide range of applications, going from cooling to solar desalinations. What all these applications have in common is that they were implemented by fibrous textiles and they regarded the optimization of the water transport within their structure. So we envisioned a fabrication process divided into 5 different steps. Starting from plastic waste, we can recycle it, then design and characterize the microstructure of a material, optimize the design of a component for a given application, and finally fabricate and implement it. So let's see how the microstructure affects the water transfer. One of the key parameters affecting wicking and evaporation is the contact angle between the water and the fibers, and it strongly depends on the surface chemistry of the material used. For this reason, we developed a theoretical model that can be easily used to measure the contact angle from images, and we used it to assess how different fabrication techniques and surface treatment affected the contact angle and so the water transport. Besides the surface chemistry, also the fiber arrangement is important, so we developed another theoretical model that was used to optimize the microstructure of the textile to achieve the best wicking properties possible. When designing a component, also the heat transfer has to be taken into consideration, as the heat and mass transfer are coupled and they depend on the microstructure of the textiles, as we have seen, but also on the evaporation and on the radiation, especially for outdoor applications. For this reason, we have implemented a finite element model to couple the heat and mass transfer, and the model was used to assess the wicking of complex 2-dimensional and 3-dimensional geometries, but also complex transients, for example the drying of a textile when exposed to the sun. In my research activity, I have focused on 2 different applications. The first one is a multi-stage passive cooler, which uses these types of material to absorb water from a reservoir and to sustain an evaporation process. The performance is achieved outperforms all the other competitors in the literature using passive devices, and so this is really a good result. The second application is personal thermal management, so we have created a garment made only by polyethylene. And this is much more sustainable than other materials commonly used for fabrics and is also completely recyclable. Thanks to its optimized microstructure, it also dries faster than other materials and is suitable for relative cooling. This is all from my side and I thank you for your attention.